In this video, we will talk about strategies for solving logarithmic equations, which is the last assignment for section 4.6. Okay, so the first type of question you might see is ones where we're solving just by using the definition of logarithms, right? And what that definition means, right, is just using the inverse relationship to exponential functions. Okay, so the first thing with this question, we're asked to solve where the log of negative 5x plus 35 is equal to 1. And the first thing, again, to note when we have this common log, right, where nothing is written, no base is written, just log, right, the implied base there is 10. So if we want, we can write that in just to remind ourselves, right? And now, again, if it says here we're supposed to use the definition of logarithms, all we need to do at this point is translate this to the corresponding exponential statement using the inverse relationship. So remember, we have to look at this, and whatever the base of our log is, we're going to use the same base for our exponential. And then what we need to do, since these things are inverses, right, we need to take this expression, which is the input of our log, and make that the output of the exponential. And this number here, the 1, which is the output of our log, is going to become the input of our exponential, right? So our equation becomes 10 to the first equals negative 5x plus 35. Right? So again, we're keeping the same base, still base 10, but our negative 5x plus 35, which was the input, now becomes the output of our exponential function, right? And the 1, which was the output, becomes the input into our exponential, right? And the nice thing about this, right, by switching to the inverse, it allows our input to become the output, right? So the x, which was trapped inside of the logarithm, is now on the outside, and now we can isolate it from here, right? So first thing is we can evaluate 10 to the first. That's just going to be 10. So next we can subtract 35 from both sides. So that'll give us negative 25 equals negative 5x. And then if we divide both sides by negative 5, we'll be left with x equals 5. And the last thing we should do before we enter this answer is just check and make sure that it's not extraneous. Because remember, with these logarithmic functions, we have a restricted domain. So we should always check and make sure that this is a legitimate input. But if we were to plug in 5 here, we would get negative 25 plus 35. That is positive, right? So it's in the domain of the log, which is all numbers greater than 0. So we can go ahead and enter that answer. Okay. And just one more example. This is another one where we just be using the definition of a log, right? So this idea of rewriting it in terms of the exponential. And here I just wanted to remind you that when we see the natural log, right, we can really think of that as the log base e. So for this one, when we switch from the log to the exponential form, again, we keep the same base. The 5 becomes our input, and the 4x minus 2 becomes our output. Right? And another thing I wanted to point out here, we can't actually compute e to the 5th, right? It's not going to be a nice finite decimal, and so we're going to leave it like that and just keep working to isolate x. So we would add 2 to both sides, and then divide by 4. So our final answer for x would be e to the 5th plus 2 over 4. That would be our exact value. And if it gives us rounding instructions, right, that's just telling us that it now expects us to put this into the calculator and come up with a decimal approximation. Okay. So that was just using the definition, right, or the inverse relationship between logs and exponentials to solve each of those equations. And there are two other main strategies that we have for solving logarithmic equations. The strategy that we're going to use here is actually similar to a strategy we used for solving exponentials, and it's just taking advantage of the one-to-one property. So if you remember, what the one-to-one property says is for a function to be one-to-one, right, that means that every input corresponds to exactly one output and vice versa. Every output has to have come from exactly one input. So our one-to-one property for logarithms just means if we have a log of any base, right, and we have one expression as the input on one side of the equation, right? So if the outputs of these two logs are equal, the only way that could be true is if the inputs were equal, right? So, or in other words, these two equations are equivalent. So what that means is whenever we have a log on both sides, right? A single log with the same base on both sides, we know that that's equivalent to just setting the insides equal, right? So since, again, we only have a single log expression on each side, and they have the same base, right? They're both base 10. These are both common logs. What that means is the very next step, we get to actually just drop the logs and set what's inside equal, right? So we get 3 times x plus 8 has to be equal to 5 times 4x, right? And now we just have a little linear equation here we can solve. So let's distribute that 3. And over here, we can multiply that out and get 20x. So if we bring everything to one side, or all the x's to one side rather, we would have 17x equals 24. So our x would be 24 over 17. Right, and it says to provide our answer as a fraction, right? We want to leave it as an exact answer. So that's the answer we would enter here. Okay. Last one here. This one we do have two logs, but notice that there's also another number over here. So we couldn't just move that log to the other side and then use the one-to-one property because of this, right? We also can't just switch it to the exponential form because that would require only one log being equal to some number. Right? So we have to rewrite this somehow first. And the way we're going to do that is recall the properties that we have for logarithms. In particular for this problem, we're going to remember the product rule for logarithms, right? Because that's the one that says if we have a sum of two different logs, right? So two logs with the same base, if we are adding those things, that's the same as the single log of their product, right? So again, we can condense this down to a single logarithm as long as we multiply what's inside. So what that's going to look like here, we keep our log base 2, but now on the inside, we're going to take the product of those two inputs. So the x plus 2 and the x plus 5. And that's all equal to 2, right? And now at this point, it's back like the first question we were doing in this video, right? Where we just have a single log equal to some number, and we can switch it to the exponential form to get these x's from the inside to the outside. Right? So we're looking at this, right? And we're going to take this whole thing, which was our input, is going to become the output, right? And this guy here, which was our output, is going to become the input in the exponential. And then remember, we just have to make sure to keep the same base. So what this is going to look like, it will become the equation 2 to the second power equals x plus 2 times x plus 5, right? So again, we kept our same base. That output became our input into the exponential, and the input of the log became the output of the exponential, right? And now what we have is just a quadratic equation, right? So it's factored, but this factored form doesn't help us, right? Factored form doesn't help us unless we have a 0 on this side. So let's see, we actually have a 4 on that side. So let's expand this out. It's going to be x squared plus 7x plus 10, right? And now if we just scoot that 4 to the other side, we'll have the equation equal to 0, and we can factor from there to solve, right? So I'm just making a little more room so we can keep solving this here. So if we bring the 4 over, we'll have 0 equals x squared plus 7x plus 6. And this is going to factor as x plus 1 times x plus 6. Right? So we're going to get two potential solutions here, right? This first factor gives us x equals -1, and the next one gives us x equals -6, right? And I'm saying potential solutions because remember what we said earlier in the video, right? With these log equations, which have restricted domains, we could potentially have extraneous solutions, right? So remember, the domain of any logarithm is only numbers, positive numbers, right? Numbers greater than 0. So that doesn't mean that we can automatically throw these out though, since they're both negative. What it means is we need to take each of these and see what would happen if we plugged it back into the original equation, right? So even though this first one is a negative value, right? If we plug in -1 here, the input of the log will be +1, and the input of this log will be +4, right? So that x is actually okay, because of the +2 and the +5 in our logs, right? But when we try the -6, right, this first one fails because -6 plus 2 is -4. That's still a negative value, which is not going to be in the domain, right? So that one is out. That is an extraneous solution. And the only solution that we are going to keep here is x equals -1.